So hello and welcome to our channel again. So today we are going to start the statistical mechanics topic, which is very important for the astrophysics one also. So let's start first of all discussing the basics of the Maxwell-Boltzmann statistics, because this is going to be a very massive weightage in the stellar dynamics. So that's why this is very important to know. So first of all, before discussing about that, what is the Maxwell distributions law? First of all, we are going to study some of the basic terminologies in the statistical mechanics, which is first of all, let me introduce to the W, which I'm going to tell you that what exactly this is. And second one is the equilibrium state. Equilibrium state. So we're going to discuss about that what is equilibrium state in a statistical mechanics and what is here W. So here W is nothing, it's the thermodynamical probability. So what is the meaning of the thermodynamical property? So if you know about the macro state and micro state, then this is particularly related with that term. So I hope that you all know about what is exactly the macro state and micro state, because these are the very basics of the statistical mechanics. So what exactly this thermodynamical probability is, we are going to discuss it first, and secondly we are going to discuss about the equilibrium state in these statistical mechanics. So let's start. So first of all, we are going to discuss about here W. So this W is defined as this W in the formula sense. Let me write in a formula. So this W is defined as the total number of microstates. Total number of microstates in a given macro state. So this is definition of thermodynamical probability. It means total number of microstate in a given macro state. So this is how we are defining the thermodynamical probability. And this thermodynamical probability is related with the equilibrium state. How? So what is the equilibrium state in the statistical mechanics? So let's study. So second, we are going to study about the equilibrium state. Equilibrium state. So this equilibrium state, what exactly this is? So let's see here. So equilibrium state is defined as the occurrence of that macro state which is maximum. So what is the meaning of this? So the meaning of this is that the equilibrium state in a statistical mechanics is that state for which the occurrence of that macro state, the probability of occurrence of that particular macro state is maximum, and that is how we define equilibrium state. And just like this, in this equilibrium state, the macro states, the occurrence of that particular macro state is maximum. Hence also our W is also maximum, which is our thermodynamical probability is also maximum in an equilibrium state, because it corresponds to that macro state which has the highest number of the micro state. So I hope you understood that what exactly I was trying to say. What is the equilibrium state and the thermodynamical probability? So I'm again repeating that equilibrium state, that macro state whose occurrence, the probability of occurrence is maximum, is the equilibrium state. And if the probability of occurrence of macro state is maximum, hence W is also maximum. So how exactly this is relationship between the maximum of the thermodynamical probability and that the maximum of the macro state? You all know about that why macro state is maximum, but if macro state is maximum, why W, thermodynamical probability, is maximum? So let's try to find out. So there's a general formula that tells us about that a probability of occurring of a particular macro state is defined as the number of microstate in that macro state. divided by total number of microstates, microstates in a system. So this is how there's a definition of the probability of the occurrence of a given macro state. So to clarify this in numbers, so let's see, I'm taking any arbitrary number which might be not correct in this real scenario, but I'm trying to prove it with the example. Suppose that we have two macro state. So in one macro state there is 5 microstates, and in one macro state there is only 2 microstate. So the probability of occurrence of the macro state of a given macro state, which means this macro state, is defined as the total number of microstate in that macro state, which is 5, divided by total number of microstate, which is 7. This is the probability of occurrence of the first macro state, and this is second. And probability of occurring of the second macro state is defined as the microstate in that macro state and divided by the total number of microstate. So from this scenario, it is well written that the probability of occurrence of this particular macro state is maximum. And if the probability of occurrence of this particular macro state is maximum, hence the thermodynamical probability is also maximum, because you know that the thermodynamical probability is the number of microstates in that macro state, which is 5, which is also maximum. So this is why, if there is a equilibrium state, in equilibrium state the thermodynamical probability is maximum. Remember, thermodynamical probability is nothing, it's just the total number of microstate in that macro state. I hope you understood, and I will try to just recap all of this particular thing. What I was saying is that equilibrium state is that macro state whose probability occurrence is maximum. And if the probability occurrence of that macro state is maximum, the thermodynamical of that state is also maximum. Then why the thermodynamical probability of that state is maximum? So I've taken an example that how we are defining the macro state. So the probability of occurrence of any macro state is defined as the number of microstate in that particular macro state in which you are finding the probability, divided by the total number of microstate in the system. And I've taken an example. Suppose that there is 2 microstate, one microstate and second microstate. So there is 2 macrostates, macrostate. So there are 2 macrostate, first and second. In this particular macro state, you can see that there are 5 microstates, and in this second macro state there are 2 microstates. Understood? Then if someone asks you that, okay, what is the probability of occurrence of this first macro state? So the probability of occurrence of the first macro state is defined as the number of microstates in that macro state, which is 5, divided by the total number of microstates in the system. And in the system, it's obvious that is 5 plus 2, 7. And the probability of occurrence of second macro state is defined as the number of microstate in that particular second macro state, which is 2, divided by the total number of microstate, which is 7. So I will write down here so you will not confuse that the probability of occurrence of first macro state, suppose that you have 2 macro state. In one macro state you have 8 microstate, and in second macro state you have 10 microstate. So the probability of occurrence of 1 is defined as the number of microstate in this particular one macro state, which is 8, divided by 10 plus 18, which is 8, which is the total number of microstate in the system. So the probability of occurrence of 1 is what? 8 divided by 18. This is just an example. Maybe this is not accurate in this real descriptions. I'm just taking an example, okay? And just like this, the probability of occurrence of your second macro state is defined as the number of microstate in that macro state, which is 10, where again 80. So this is how we define their probability of occurrence of any of the macro state, and if this is maximum, then the W is maximum. So these are all the basics of what I have discussed here about the macro state and micro state. Now let's move to the derivation of the real Boltzmann law, which is the distribution law derivation. Distribution law. Now we are going to derive it because I have met the basics that you require for this particular derivation. So let's start. So I am taking this distribution law in the equilibrium state, and I have said that in equilibrium state, first of all, W is maximum and the total number of particle Ni's over summation Ni is equals to N. It means it is a constant and it should be equal to the N, and the energy should also be constant. Ei Ni is equals to the total energy, which is also a constant. So there are two constraints that we have taken in this particular macros, in this particular state, which is the total number of particles should be constant and the total energy should be constant. There are two constraints, okay, and you will see that while deriving this we will use this particular constraint. How? So let's see here. So W, how we define the thermodynamic probability in this mathematical form. So it is equals to the n factorial divided by n1 factorial into n2 factorial into n3 factorial, where n is the total number of particle, n1 is the 1 particle, 2 particle, 3 particle, and it goes till ni factorial. So I'm going to take the log, and if you ask me why I'm taking the log, the fact is that it will reduce the mathematical complexities to derive the distribution law. That is the only answer that I can give you, that why I'm taking the log. So log on both sides will yield that log of W is equals to the a well-known formula of the log n factorial, and it will equals to minus summation over I L log Ni factorial. Okay, so this is how we are going to define in this particular form. Now there is a very well-known formula which we will give, which is the Stirling's theorem, which tells us that this is a particular theorem that I'm going to apply here, which tells us that log x factorial is equals to nothing, it's log x minus x. So this is the particular property I'm going to use. This is the Stirling's theorem. This is the particular Stirling's theorem, and we will apply this here, where the base should be E. Remember, the base should be E, okay, and this is the particular formula. So now let's apply this in this particular scenario. So what will we get is that log of W is equals to the n log n minus n minus, and if you apply this is Ni log Ni minus Ni. So this is how we defined it, okay. Now we are going to take the derivative of this particular equation with respect to the Ni, which means the number of particles. So if I take the derivative, there are two terms here. N is a constant, so let me choose some another color. When I will take the derivative with respect to the Ni of log of W, what will yield is that this particular term is whole constant and it will become 0, and what we are left is with the calculations of only this particular type of, let me clarify it here because you might, this is into sign and this is negative sign, okay. So to avoid confusion, I'm writing it again, because this is Ni into log Ni minus Ni, okay. So this is the particular formula, okay. When you do the derivative of this, you are going to apply here some of the rules of this derivative, which is equals to the summation here and negative, ni into log ni minus ni, and if you know the integration chain rule, sorry, when you know the differentiation of chain rule, it is equal to ni into 1 divided by ni, and it is equals to then the positive of the ni and log, which will yield 1 log ni and minus 1 summation over I. Okay, now if we write it as del by del ni of log of w, which is thermal probability, you will say that this is equals to 1, and this will cut out. What we are left is with this particular equation as summation of I log ni. So this is what I left it with. Okay, so now we are here with one equation. Remember the two constants that I have introduced in the beginning? What were the two constants? If you remember, the two constants were that summation over I should equal to n, total number should be constant, and first constraint. The second constraint was that ni into ei, summation over I, should be also equals to the constant. So when we take the derivative of this particular term with respect to ni, summation, it will yield 1, and then we'll do derivative over ni of this particular summation ni into ei, it will yield ei. So to solve this equation, I'm introducing the Lagrange multipliers, which you will study in the general Lagrangian mechanics. So I'm not going to talk about the Lagrange multipliers in this particular video. So the method of Lagrange multipliers was that to multiply with the particular constants. What I mean is that what I have done is that the derivative which I get was the log of ni. What we'll do is that multiplying this particular equation with some constant, let's say alpha, and this particular constant with some beta, let's say. So what I will get is that it is equals to plus alpha plus ei into beta is equals to 0, because the derivative when you will take is equals to 0. Of course, you know that the derivative will equals to the 0. So this is how we defined our equations. Now what we are going to do is that log of ni should be equal to negative of alpha and negative of ei into beta, where alpha and beta are some sorts of constants. So now we are going to remove the log, and the equation that we are left with ni is equals to the e to the power negative alpha into negative e raised to the power iota beta. Now the next thing is ni is equals to, let's separate it, e to the power negative ei into beta. Now what I'm going to do is that I'm taking a small assumption and taking e to the power minus e alpha as some constant a. So let's see what will happen. It will be like ni is equals to a e to the power negative ei into beta, and this is our equation that I was trying to derive it, and it is a very important equation. And this is the distribution law of the Maxwell and Boltzmann, which tells us about the relationship between the number of the particles as the function of an energy. Number of particles as a function of energy, this particular equation tells us. And this fundamental equation, then we will use this particular equation in next video to derive the probability. But what probability? To derive the probability of occurrence, it means to derive that how many particles are in the ei energy state. We are going to derive this and find out the probability and what's the expression of the probability. So this is all for my today's videos, where I discuss about all of these basic terminologies in the statistical Boltzmann law. And let me know if you want some another topic or some basic topics in the statistical mechanics, like what is macrostate and microstate. I haven't told this in particular video because these are the very basics knowing about the macro state and the micro state. So in the next video probably we are going to discuss about how to derive out the probability that how many particles are in this EI state, E1 state, E2 state, and these are very important because the statistical mechanics is made to understand that how to govern the principles of physics while there are so many large number of particles. And this is our first step, and this is our first very important equation which tells us about the number of particles as a function of energy. So this is all for the today's video. I hope you understood all of that stuff, and if you are any confusion about that what I have done here, you should write in the comment section. I will try to read your comments, and thank you for watching my video.